Okay. Now, I can hardly contain my Archimedean zeal, okay? I think that Archimedes, and I may or may not ask you about this at some point in the future, I think Archimedes is one of the most profound mathematical minds to ever live. He clearly was a little bit crazy, and I'll read you some things from the chapter, and I hope you indulged yourself in that. I'll read you some specific things from the chapter that speak to that. I mean, he was just a very interesting character, kind of a prototypical mathematician, if you will. But he was also acutely interested in things like pulleys and levers, lots of, hydrostatics and things like that. But he was just an extraordinary character for sure. And honestly, it's amazing that he was able to do some of the things he did with the tools that were available to him, including notational tools and definitional tools. He just saw stuff and was able to kind of write it down. Sometimes he had a hard time explaining what he meant or how he knew it. But he was an amazing guy. Okay, so let's talk about him, shall we? So again, he was born in the 3rd century BC in Syracuse. His father was an astronomer. He was really, and because of that, he was really interested in the cosmos. Okay, looking at stars, mapping patterns, thinking about predicting. I mean, he even did interesting things like calculate distances in a non-Euclidean way. From between cities that were far apart from one another. Because as you know, the Euclidean geometry, as we've discussed, is kind of a flat planar geometry, right? And it starts to fail in terms of its accuracy once you start moving across larger distances. And Archimedes was fully aware of that, even though this was 3rd century BC. So he would have been operating in a more, like a pretty rudimentary form of what we would call the spherical geometry. When you look at those napkins on planes that, like, if you're on Southwest or whatever airline you're on, and you see all these plane routes on the napkins, have you ever seen that sort of thing before? What do you notice about all those routes? Yeah, they kind of are curved like that, right? And the reason it's that way is because you're kind of imposing a spherical geometry on a flat planar surface, yes? And that makes those little arcs, really stand out. But indeed, that still is the shortest distance, even though it looks like an arc. It's sort of strange, right? Okay. There's this large writing called Life of Marcellus by Plutarch that is basically the source of most of what we know about Archimedes. Okay, and some of the passages that are in the book are directly from that writing. He was in Egypt as a boy. He studied at the library at Alexandria, one of the most famous libraries in the history of the world. He was trained in the Euclidean tradition, and as I mentioned, he was sort of the prototypical mathematician. I wanted to read this brief passage right here. It says, we learn from Plutarch that Archimedes would forget his food and neglect his person to that degree that when he was occasionally carried by absolute violence to bathe or have his body anointed, he used to trace geometric figures in the ashes of the fire and diagrams in the oil on his body, being in a state of entire preoccupation and, in the truest sense, divine possession with his love and delight in science. That's from Plutarch's writings, just describing the person of Archimedes. And Dunham says, this passage portrays the stereotypically absent-minded mathematician, not to mention one to whom cleanliness was next to irrelevant. Of course, the most famous absent-minded story concerns the crown of King Hieron of Syracuse. The king, suspicious that his goldsmith had substituted some lesser alloy for the crown's gold, asked Archimedes to determine its true composition. As the story goes, Archimedes wrestled with the problem until one day, during what must have been one of his rare forced baths, he hit upon the solution. Jumping from the bath, he ran through the streets of Syracuse shouting, Eureka, Eureka! Unfortunately, so absorbed was he in his wonderful discovery that he forgot to don his toga. What the townspeople thought at seeing their fellow citizen running stark naked in their midst is impossible to say. Pretty classic passage about Archimedes. You may have heard, that of his discovery of how to measure density. It occurred to him while he was in the bath, and he just didn't bother to put on his toga when he ran out in the streets to announce his discovery. So there you go. One of his most famous treatises is called On Floating Bodies, which discusses the principles of hydrostatics. And there's a certain kind of water pump he invented, and actually my kids did this one time. It's called the Archimedean screw. And there's a picture of that right there. It's a way to kind of move water from a lower position to a higher position. You can kind of see how that thing works. Okay, it's still in use today. Guys, can I ask you to mute yourselves on there? I think I can do it myself, but I'm just going to ask you to kind of mute yourself if you would. And again, he was instrumental in the development of pulleys and levers, optics. He was just involved in lots of different areas of physics and science, mathematics, of course. Okay. And this is one of the most intriguing stories about Archimedes. There was a famous siege by the Romans. They invaded Syracuse. It's a Roman general by the name of Marcellus who was in charge of that particular siege. And actually, it was Archimedes' ideas that really came to the aid of Syracuse. And Syracuse was almost this impenetrable force because of the weapons that Archimedes' ideas had been kind of leveraged into developing. He helped to prepare the city for attacks. And again, eventually, there was a time when the Syracusans dropped their guard during the Feast of Diana, and that was kind of the Romans' opportunity. But I wanted to read a little bit. This passage is a little bit longer, but man, it's so worth it. I'm gonna go ahead and read you the specifics about the siege of Syracuse. According to Plutarch, the Roman legions marched to the city walls, believing themselves to be invincible. And this is from Plutarch's writings, this part. But when Archimedes began to ply his engines, he at once shot against the land forces all sorts of missile weapons and immense masses of stone that came down with incredible noise and violence, against which no man could stand. For they knocked down those upon which they fell in heaps, breaking all their ranks and files. And the Roman naval forces fared no better. For huge poles thrust out from the walls over the ships and sunk some of the great weights which they let down from on high upon them. Others they lifted up into the air by an iron hand or beak. And when they had drawn them up by the prow and set them on end upon the poop, they plunged them to the bottom of the sea. Or else the ships, drawn by engines within and whirled about, were dashed against the steep rocks that stood jutting out under the walls, with great destruction of the soldiers that were aboard them. By the way, there's lots of stories about Archimedes taking bets about lifting massive weights with his levers. He actually apparently he took a bet at one point that he could actually lift up a ship by himself using one of his levers, and nobody believed it, and he just went really far away and set up a lever and actually did it. He actually was able to move this ship by himself, one of his levers. Such destruction, related Plutarch, was a dreadful thing to behold, and one is inclined to agree. Under the circumstances, Marcellus thought it prudent to retreat. He withdrew both land and naval forces to regroup. Holding a council of war, the Romans decided upon a night assault, in the expectation that Archimedes' devilish weapons would be useless if the attackers slipped too close to the walls under the cover of darkness. Again, the Romans had an unpleasant surprise. The diligent Archimedes had arranged his devices for just such an eventuality. And no sooner had the Romans crept up close upon the fortifications than stones came tumbling down perpendicularly upon their heads, and as it were, the whole wall shot out arrows at them. In response, the terrified Romans again retreated, only to come under attack from Archimedes' longer range weapons, an attack that inflicted a great slaughter upon them. By this time, the vaunted Roman legions, seeing that indefinite mischief overwhelmed them from no visible means, began to think they were fighting with the gods. It is perhaps an understatement to say that Marcellus had a serious morale problem. He demanded of his shaken troops a renewed courage to continue the assault, but the previously invincible Romans wanted no more of it. On the contrary, the soldiers, if they did but see a little rope or a piece of wood from the wall, instantly would cry out that there it was again. Archimedes was about to let fly some engine at them, and they turned their backs and fled. Knowing that discretion is the better part of valor, Marcellus chose to abandon the direct assault. Instead, trying to starve the trapped Syracusans into surrender, the Romans began a long siege of the city. Time passed with no change in the disposition of forces. Then, during a feast to Diana, the city inhabitants, given up entirely to wine and sport, became careless about guarding a section of the wall, and the opportunistic Romans had their chance. Their armies broke through the lightly guarded section and poured into the city in a vicious and destructive mood. Marcellus, surveying the beautiful town, is said to have wept in anticipation of the havoc that his men were sure to wreak. But it was the death of Archimedes that brought Marcellus his greatest sorrow, for he had come to respect this gifted antagonist. According to Plutarch, as fate would have it, intent upon working out some problem by a diagram, and having fixed his mind alike and his eyes upon the subject of his speculation, Archimedes never noticed the incursion of the Romans, nor that the city was taken. In this transport of study and contemplation, a soldier right there in that picture, unexpectedly coming up to him, commanded him to follow to Marcellus, which he declining to do before he had worked out his problem to a demonstration. The soldier, enraged, drew his sword and ran Archimedes through. Thus ended the life of Archimedes. He died as he lived, lost in thought about his beloved mathematics. We can regard him either as a martyr to his research or as a victim of his own preoccupied mind. In any case, mathematicians may come and mathematicians may go, but no other has had an end quite like this. Little interesting passage about the end of Archimedes' life. He was an old man at that point, but actually there are other historical documents that talk a lot about what happened to this soldier that did this to Archimedes. Apparently, Marcellus actually had this soldier executed for doing that. Yes, sir. He invented all sorts of catapults, like ones that kind of slung massive boulders and kind of used weights and levers to pull it off. You ever seen those sling catapults that like throw boulders and things like that? Yes, he invented several of those types of things. I don't know that he was intent on inventing weapons per se, but a lot of his inventions were leveraged to that end. Yeah, there you go. You got it. You got it. All right, let's talk a little bit about the circular area pre-Archimedes, okay? We've already talked about how the Greeks knew that if you took the ratio of a circle's circumference over its diameter, that was equal to a constant. Right? They weren't really sure exactly what that constant was, but they gave it a name, pi, okay? They knew, again, if I take any circle, every circle is similar to every other circle, right? Every circle is just a blown up version of every other circle. And therefore, if I take a circumference and divide by the diameter, that ratio will be preserved all the time. And they called that constant pi. A proposition from book 12, number 2 of the elements states that the ratio of circular area to the diameter squared is a constant. So they knew that that was true. They knew that if you took the ratio of any circle's area to its square of its diameter, you always got the same number also. But they didn't really know that there was a connection to pi in both cases. Does that make sense? Like, we know that the area of a circle is pi times the radius squared, right? And we also know that the circumference of a circle is equal to pi times the diameter. But what the Greeks did not know at the time is that there was any connection between the formula for the area of a circle and the formula for the circumference of a circle in terms of the constants that were produced. Does that make sense? And that's where kind of Archimedes really surprised everyone with his formula for the circular area. Okay? one thing that we need is the area of a regular polygon, the formula for the area of a regular polygon that involves something called the apothem and the perimeter, okay? So the apothem, what is it? Okay, so here, let me kind of draw a picture of a regular polygon here, and I'll explain what's going on here. So like here's a regular pentagon, or it's, you know, supposed to be regular, okay? It's a regular pentagon, okay? What the apothem was is you kind of drew a point right in the center, and the apothem was kind of the height here, okay? So this is H, okay? And then of course Q was the perimeter of this thing. Now, if you think about it for a second, this formula makes perfect sense because look, you can kind of break up, right? You could break up this thing into 5 triangles. Do you see what I'm saying here? And you could compute the area by simply doing 1/2 base times height for each one of those triangles and adding them together. You see what I mean? But if I add all the bases together, what's that going to give me? It's going to give you the perimeter. Does that make sense? And all of those are going to be multiplied by 1/2 times the apothem, or the height of one of those triangles, yes? So that's where this little formula comes from, okay? Basically, you factor out the 1/2 times the apothem, and you basically have added up all the bases, but adding up all the bases is just the perimeter. So that's where this formula comes from. Any questions on that? Okay, so that's like a clever little formula that the Greeks would have known well. So 1/2 the apothem, which is basically the height of one of the triangles that you get from subdividing the regular polygon, and then you multiply it by the perimeter, and that gives you the area. Okay? Any questions so far? Okay. Moreover, I mean, and this is just sort of obvious, if you inscribe a polygon, okay, if you inscribe a polygon, so like in a circle, okay, so here's a circle, and suppose I inscribe a polygon, okay? Okay, that's an inscribed fivegon, yes, an inscribed pentagon. And they knew that an inscribed polygon would have area less than the circle, right? Obviously. And similarly, a circumscribed polygon, so like here's a circumscribed square, for instance. Okay, see the circumscribed square, okay? Obviously, a circumscribed square has area bigger than the circle that it circumscribes. You see what I'm saying? Okay, there's just a fairly obvious thing, but also, let me ask you something. What about the perimeter of the circle? How does the perimeter of the circle compared to the perimeter of the inscribed polygon? Which one's bigger? The perimeter of the circle, i.e. the circumference of the circle, or the perimeter of that fivegon that's inscribed? Circle, obviously. And what about the circumscribed polygon? How would that perimeter compare to the circumference of the circle? Bigger, clearly. Okay, and Archimedes is going to make use of both of those facts. In fact, here's what's amazing. Archimedes is really going to be doing an early form of calculus 2,000 years before Newton kind of hashed all that out, okay? In fact, we'll talk about Newton at length, but Archimedes is going to do something which looks like a limiting process 2,000 years before lots of notation existed. He had something called his method of exhaustion, where he would try to approximate things with things that he knew. And it was essentially an early form of calculus, okay? So I think Archimedes should be lumped into the group of guys that invented calculus, okay? He was just simply 2,000 years ahead of his time, okay? Archimedes, and then you have Newton and Leibniz later on in the 18th century, right? But let's give Archimedes a little bit of credit here, okay? Moving on, here it is, measurement of a circle. The area of any circle is equal, okay, look, this is sort of bizarre. The area of any circle is equal to a right-angled triangle in which one of the sides about the right angle is equal to the radius and the other to the circumference of the circle. Okay, what in the world is Archimedes talking about? Well, he's saying you take a right-angled triangle. Okay, I have a circle here. Okay, this thing has a particular radius r and a particular circumference c. What he's saying is, hey, the area of this circle is the same as the area of a right triangle with one of its legs equal to the radius and the other of its legs equal to the circumference. Yeah? So, and the Greeks would have immediately known the formula for the area of that triangle. The formula for the area of that triangle is A equal to what? 1/2 RC. Okay, and of course, since we know that C is equal to, okay, how does C relate to the radius? It's 2 pi times the radius. Do you know what I'm saying? This would be 1/2 r, and then it would be 2 pi r. And lo and behold, the 2's cancel, and we get pi r squared. Amazing. Yeah? So what Archimedes is claiming in this proposition is basically that he knows the formula for the area of a circle. Okay? And he's kind of doing it in a weird way. He's sort of saying it's going to be the area of this triangle. Okay? That happens to have one of its right triangle that has one of its legs equal to the radius and the other leg equal to the circumference of the circle. Yes. Oh, sure. Go for it. Yeah. Okay. All right. Any questions on that? You better hurry back though, man. It's going to get exciting here in just a minute. Okay. So let's get to it. Okay. Now, he started with 2 figures. Okay, one was a circle with center O and radius R and circumference C. So I'm just going to kind of draw a picture here. It's going to be our working picture. Okay. So here's R, here's C. Okay. Let me move this out of the way so you can see this thing. You know? Okay. And also this right angled triangle, okay, so the thing that we've been talking about here, okay, so here it is, you know, this right angled triangle. I'm just going to draw this thing again. One of its legs is R and the other one is C. Yeah? The area of the circle is what he called A. Okay, so this thing has area A. Okay? And the area of the triangle he called T. Okay, so this area he's calling T, or triangle, yes? Okay. And of course, the goal is to show that A is equal to T. Does that make sense? If you can show that the area of the circle is the same as the area of that triangle, we're done, yeah? And by the way, then you would have the formula for the area of a circle as we just surmised on the last slide, okay? So he's going to seek to prove that A is equal to T. And to do so, Archimedes is actually going to use a so-called double reductio ad absurdum. Okay, what does reductio ad absurdum mean? We talked about that during one of Euclid's proofs. Reduced to an absurdity. So it's basically a proof by contradiction, yeah? So what he's going to do is he's going to assume something and show that that assumption was not good, that it led to some kind of nonsense, in fact, a contradictory statement. And therefore, the assumption itself must have been faulty, okay? So if he wants to prove that A is equal to T, what would be kind of the opposite of that? A does not equal T. In which case, there are 2 possibilities. What are the 2 possibilities? If A is not T, then what are the 2 possibilities? Yeah, A is greater than T or A is less than T. Those are going to be the 2 possibilities. And that's why it's a double reductio ad absurdum. He's going to deal with each one of those cases separately. Does that make sense? Okay. All right. So let's get to it. Okay. So I have these 2 things. I'm going to draw some other pictures over here, though. Okay. Case 1. Again, remember, he's going to assume the opposite of what he wants. Namely, he wants to show that the area A of the circle is equal to the area T of the triangle. Okay? Well, if A is greater than T, that means that A minus T is positive, right? Yes? I mean, you just simply subtract T to the other side. It means that A minus T is positive. Yes? Okay, so that's going to be an assumption we're going to use here in a minute. So Archimedes knew, okay, if I start with a circle like this, then what he can do, now remember, so we're assuming that A minus T is greater than 0, right? So there's this A minus T is equal to some positive number. So what he did is he's going to start taking out his compass and his straight edge. He's going to start by inscribing a square, and then he's going to subdivide the edges of the square and create, let's see, basically something that has twice as many sides, like an 8-gon, for instance, yes? And then continually subdivide the sides and continue to inscribe a higher and higher number of sided polygon, yes? And eventually, that polygon is going to have so many sides that it's going to be pretty close to the circle from the inside. Does that make sense? And in particular, he can do that to such an extent that the difference between the area of the circle and the area of that inscribed polygon is pretty small. Does that make sense? So what he did is look, I know that the polygon that he is constructing is probably much smaller than this, or has a lot more sides than this. But like, suppose that that's the polygon right there. Then again, we have A for the area of the circle, and what he called the area of the polygon Z. And what he wanted is the area of that polygon to be so close to the area of the circle. And by the way, is it smaller or bigger than the area of a circle? Smaller. So close from below to the area of a circle that the difference between A and Z was actually smaller than the difference between A and T. Yes? And you can do that by putting enough sides in there that the difference between the circle and the polygon in terms of area is actually smaller than whatever that positive number was, A minus T. Does that make sense? Does that not sound like calculus to you? That's like a limit process, yeah? It's going to continue that. So in other words, he does it in such a way that A minus Z is actually less than A minus T, yeah? And do you guys realize that you can kind of rearrange that? You can add Z to both sides, add T to both sides, you can subtract A from both sides, and eventually you get that T is less than Z. You see that? Yes, sir. T is the triangle. Right, remember, so T is like T is this triangle. So this is R and this is C, right? And this guy right here, right, you have R, and then of course, the area of the circle is A, but the circumference is C, yeah? Does that make sense? So T is the triangle, A is T is the area of the triangle, A is the area of the circle. We're assuming, we want to show that A is equal to T, but we've assumed here in this case that A is actually bigger than T. Does that make sense? And so A minus T is positive. And then Archimedes' plan is to then construct a polygon from the inside that is actually closer to the area of the circle than, than the triangle is to the area of the circle. Yeah? So do you guys believe that this is possible to do this? Like you just build this polygon from the inside so the area difference is so small that that difference is actually smaller than the difference between A and the triangle. Yeah? Yeah? Okay, so that means that T is less than Z. If you just rearrange this thing, right, you kind of move Z over, move T over, and then you cancel the A's from both sides, yes? And you get that T is less than Z. Okay? Interesting. So A minus Z is less than A minus T. That implies that T is less than Z. Now hang on. But this is an inscribed polygon, for crying out loud. Yeah? It's an inscribed polygon. Therefore, the perimeter of the polygon, Q, is less than the circumference of the circle. Yes? And how do we compute the area of And how do we compute the area of that polygon? Well, remember we had the formula. It's 1/2 times the apothem times the perimeter. Yes? Where is the apothem in this thing? Like the radius is right here, correct? Where is the apothem? It's right there, right? There, that's the apothem. What's the relationship between the apothem and the radius? Which one is longer? Radius is clearly longer, yeah? So look at this. Z is equal to 1/2 times H times Q, right? Q is the perimeter of this, right? Q is the perimeter of that polygon, yes? Z is equal to 1/2 times the apothem times its perimeter. But clearly that is less than 1/2 times R times C, yes? Because the apothem is less than the radius, and the perimeter of the polygon is less than the circumference of the circle. But hello, right? So this thing is less than 1/2 R times C, but isn't that just the formula for the area of the triangle itself? Yeah? So what do we have? We have that T is less than that polygon area, that the triangle area is less than the polygon area, but what else do we have? We have T is less than Z, and what else? Yeah, T is greater than Z. That's a contradiction. You know what I'm saying here? So what he did is he kind of approximated this thing from below so that A minus Z is less than A minus T. Rearrange and you get that T is strictly smaller than Z. But on the other hand, if you just do the computation with the formulas, you get the inequality in the other direction. That's a contradiction. Yeah? Both of those two things can't be true at the same time. So the conclusion here is it possible for A to be bigger than T? Or is it possible for the area of the circle to be bigger than the area of the triangle? No, that led to nonsense, right? That led to a contradiction, okay? Right, are you ready? So what's the only other possibility we would have to consider? What do you think? Yeah, A is less than that thing, okay? So the only other possibility is A is less than T. But then that would mean that T minus A is positive. Okay, remember, so T, once again, just so we don't lose track of what's happening here, T is the area of this right triangle, yeah? So here's R and here's C, right? T is the area of this triangle, okay? And then I kind of draw the circle again. Here's R, here's C, right? And the A is the area of this thing, okay? This time, what do you think Archimedes is going to do? In the last one, we inscribed something. What do you think he's going to do this time? Circumscribe, right? So, I don't know, I'm just going to do a square here. Okay, circumscribe this square. Okay, now here's what's interesting. In this case, okay, and so the perimeter of this thing is Z, by the way. In this case, or actually, no, not the perimeter of the perimeter of this thing is Q. The area of this thing is Z. Okay. In this case, what do you notice about the radius and the apothem? Yeah, so H is actually the same as the radius. But what about the circumference of the circle and the perimeter of the circumscribed polygon? The perimeter is actually bigger. Does that make sense? Okay, so once again, he's going to do the same thing where he circumscribes about the circle a regular polygon with area Z that exceeds the circle, because the area of those things is bigger than the area of a circle, right? That exceeds the circle by no more than T minus A. T minus A is a positive number, yes? So in other words, what he's saying is he's constructed this polygon in such a way that the difference between the circumscribed polygon and the area of the circle is smaller than the difference between the triangular area and the area of a circle, yes? He just kind of continues to subdivide that in such a way that that happens. And when you rearrange that, actually all you have to do is add A to both sides this time, and you get that Z is less than T, yeah? But if you just go and compute the area the old-fashioned way, excuse me, namely with like Z, if Z is the area of this polygon, it's gonna be 1/2 times the apothem times the perimeter, yes? But what's true about the apothem? What is it actually equal to this time? The radius. And what's true about the perimeter? It's bigger than the circumference. So that's why this thing is going in this direction, yeah? So it's greater than 1/2 RC, which is the area of the triangle. So look at this. Here I get that Z is greater than T. What? So look, Z is less than T and Z is greater than T at the same time. Impossible. Okay? That's the contradiction. So what got us into this mess? Well, we assumed that the area of the circle was smaller than the area of the triangle. And Archimedes was able to come up with a contradiction, yes? So are either one of these possibilities, or either one of these cases possible? No. Archimedes has shown that they absolutely can't happen. So what's the conclusion? A is equal to T. And that's it, right? And he immediately gets the formula for the area of a circle. You guys should be pretty excited about that. I don't know about you, but I mean, I'm going to feel pretty good for the rest of the day here. All right. Questions on that? Promise, like, go think about it. It's pretty clever. Yeah.
So, like, he pulled the regular polygon that he was trying to make.
Mm-hmm.
Like all these sides. He just kind of pulled that out of nowhere, right?
Mm-hmm.
Like, well, if I do this.
Yeah, that's right. That's the sort of guy Archimedes was. He didn't have to be told what to do. Yes. He did. He used a 96-sided polygon. Well, because he did a specific example. Like he did a specific example where he was like, well, what if I find myself in this situation where the tolerance is this much? And then he did a 96-sided polygon to actually show that he could pull it off. Yeah. Other questions? Somebody had their hand up over here. All right. And this is just me kind of reiterating what we already wrote down. He said that the formula for the area of a circle is the same as the formula for the area of that triangle, which is 1/2 times r times c, yes? You just plug in that c is equal to 2 pi r, you get pi r squared. This was shocking to the Greeks. They were like, what? The same constant? It's the circle divided, or the circumference of a circle divided by the diameter. It's the same constant for the area of a circle. That was a massive shock. And that it's the same constant. And they would have seen this as, you know, somewhat kind of spiritual or mystical in some way, right? We've kind of talked about that before. Okay. I wanted to talk a little bit. We have a little bit of time here. I don't know if we'll get through all of this, but I want to talk a little bit about other things that he did. Now that the Greeks had seen that pi was kind of at the center of not only the formula for the circumference of a circle, but the formula for the area of a circle, clearly pi was a big deal. You know what I'm saying? And so it's like, well, what is pi? And what Archimedes did, and actually he did the 96-sided polygon again. He used a 96-sided polygon to actually estimate what pi was. Okay? And he actually found out by doing circumscribing and inscribing of polygons, he was able to zero in on the value of pi and said that it's somewhere between 3 1/7 and 3 10/71. It's fairly impressive, right? By the way, 3 1/7 is the same as 3 10/70. You know what I'm saying? Yeah? That's pretty good, especially given the sort of tools he would have had available to him notationally. Zeroed in on pi fairly well. I mean, you could actually approximate that. Can someone actually plug that into your calculator? Like, what is 3 1/7 equal? 3.142? What about 3 10/71? Ah, so he's got the first 2 digits of pi. That's fairly impressive, if you think about it for a second, right? Now, it'll take us until chapter 7 when we look at Isaac Newton Isaac Newton's going to blow everybody out of the water. Once he kind of brings the full-throated tools of calculus to full fruition. And then he's going to just blow all previous approximations for pi out of the water. Yes, he used the 96 gon for this, but he also had used the 96 gon to illustrate his proof technique. By the way, he had to actually approximate square roots at certain points in his calculation, which would have been horrendous back then, for sure. And I'm not just talking about like the square root of 2. It would have been the square root of some nasty stuff, right? So, this guy's amazing for sure. I wanted to actually just articulate like a brief history of pi. Incidentally, there's a passage in 1 Kings 7:23, which is actually the first recorded estimate of like historical recording of an estimate for pi. Essentially what happens, like you're talking about this sea, they call it a sea, it's essentially a giant pot that was built. And they measured it in, what are these things called? I always forget what they call these things, huh? Cubits. And they did a measure of cubits around the edge and across the center of the thing. And they gave a specific number. And it turns out that if you divide the one by the other, I think it was 30 cubits around and 10 cubits across. And of course, if you take 30 divided by 10, which is the circumference of the sea, divided by the diameter, what do you get? 3. So there's an early approximation to pi right there, but they were just kind of doing it with like a thing that they were going around with, yes? Archimedes, 760 years later. Ptolemy, about 400 years after the fact. After that, 390 years. And then you have kind of sporadic estimates that improve upon previous estimates for pi. All the way, there's sort of, during the Middle Ages, there's very few, there's not very many advances that are actually made in general in mathematics. But estimates for pi weren't very numerous either. 1429, Al-Kashi. Vieta was a pretty famous mathematician, 1579. And then all of a sudden, there's like a whole slew of new estimates or better estimates for pi that kind of emerge. And then I kind of capitalize Isaac Newton in 1671. We'll talk about that specifically in chapter 7. Again, the reason there was such a pi obsession was because now people realized that pi was involved in both the area and the circumference of a circle formula. Yeah, that was a shock. Isaac Barrow actually gave a really good estimate for pi at some point. He had a really clever way of doing it using some of the Newtonian calculus techniques. Legendre, very famous mathematician. There was a group effort among the French Academy of Sciences at one point in 1755. So Rutherford in 1853, that's an interesting one. Lindemann, very famous mathematician, he was the one that actually first proved that the circle is not squarable. Remember that? Yeah? There's also some other group efforts, and look, this is just going all the way almost to modern day here, and at this point we have computational machinery that can just give us approximations to pi to any degree that we want. One last thing I would mention is that Archimedes was really interested in kind of three-dimensional geometry as well. He considered the sphere and cylinder to be his masterpiece. I mean, honestly, measurement of the circle, he considered that to be fairly easy, even though it sort of shocked everybody. On Monday, I'm actually going to show you a video, which is him coming up with a way to actually measure the volume of a sphere. And the way he did it was amazing. And there's a video that kind of shows the way he carves up certain shapes, and he uses weights and levers to actually prove the formula for the volume of a sphere. But one of the things he was most obsessed with was this sphere embedded inside of a cylinder. So it's a cylinder of height 2r and radius r, and you have a sphere of radius r embedded inside of it. There was all kinds of amazing relationships that he proved about this cylinder as it pertains to the sphere. In fact, I'm going to kind of skip ahead here. Right here. He actually asked, and it's kind of hard to see on here, but if you Google it, you can see Archimedes' tomb. And on his tomb, he actually wanted a picture of this sphere embedded inside of a cylinder. And that tomb is actually there to this day, and you can kind of see remnants of that thing. I think you have to zoom in to like the place right over the entryway right there or something. Interesting guy for sure. And this was one of the results he was most proud of. The volume and surface area of the cylinder is half again as large as the spheres. And so he was really proud of that, that this like 3:2 was kind of the ratio of surface area and volume of each one of those. So he was pretty proud of that. All right, that's all I have. But actually on Monday, we're going to watch this little video that has to do with his coming up with the formula for the volume of a sphere. It's an amazing, amazing little thing. That's all for now.